Guardium data protection is built on a scalable architecture that uses agents to gather information on database access, collectors to collect and process the information, aggregators to centralize information, and central managers to manage it all. Data exists in many different places: known database servers, unknown database servers, containers, private clouds, and public clouds. Guardium must protect this data wherever it exists. In this lesson, you learn about the data sources Guardium uses for active and passive monitoring. You learn about STAP agents, ETAP agents, universal connectors, and streaming application programming interfaces, or APIs. Guardium protects data across diverse environments. It applies policy enforcement and management and centralizes major data sources, including databases, big data, files, mainframe, and cloud data sources. Deployment options are flexible. In this slide, you'll see an overview of the methods for monitoring data. We'll discuss them in detail in later slides, but for now, here's a summary. STAP agents are installed on database servers, generally one STAP to a server, and monitor all of the databases on that server. External STAP agents, or ETAPs, are used for containerized and cloud-based sources. Both STAPs and ETAPs provide real-time database activity monitoring and are usually the best choice for keeping close watch over highly sensitive data. Agentless options include universal connector plugins and cloud event streams. These agentless options work with third-party clouds where you can't install an agent and are better for passive monitoring of less sensitive data. The Guardium STAP is a lightweight software agent installed on database servers. STAP monitors database activity, forwarding that information to the Guardium collector. Information collected by the STAP forms the basis of Guardium traffic reports, alerts, visualizations, and so on. The STAP agent can also receive control signals for the following functions. Filtering information before sending it to the collector. This reduces network traffic and collector processing load. For example, the STAP might not send information about sessions by trusted users. Blocking connections. Masking or redacting information returned by the query. STAP generally accounts for between 1% to 3% of CPU usage. In most installations, this does not affect performance. The STAP is a daemon in the user space. It has two submodules. The kernel tap, or KTAP, is a kernel module that intercepts all communications between database clients and the database server. This communication includes both local activity and network activity. KTAP monitors the Database Management System network port. Different versions of Linux and Unix kernels require different KTAP versions. The Application Tap, or ATAP, monitors communications at the application level between internal components of the server. ATAP uses KTAP to pass traffic to the STAP. STAP also integrates with database exit libraries. An exit library, such as db2exit, is a dynamic linked library that is loaded during database startup. db2exit can communicate directly with STAP. The exit method has a smaller footprint and requires less configuration than KTAP. Sometimes you can't install an STAP agent on a database server. For example, when you are using database as a service, in which case you can't access the underlying infrastructure. Or when your database is running in a container which lacks the infrastructure to support an STAP agent. In this case, use the external STAP or ETAP. The ETAP uses STAP technology in a Docker container and provides many of the same functions, including monitoring traffic and controlling database sessions. Sometimes you just can't use STAP or ETAP. How would you enable an agent on Amazon S3? In this example, you need to gather data from the Amazon S3 default activity logs. The universal connector is lightweight and open source. It is a framework that you can use to develop a plugin. This means that for any data source that has some activity or audit log, you can create a plugin to receive the events from the activity logs, parse them to put events in a standard format understandable by Guardium, and forward them to Guardium for further processing. Connectors for many data sources, including Amazon S3, MongoDB, and MySQL, already exist. You can also write a custom plugin for a wide variety of data sources. Remember that Universal Connector plugins do not have all the functions of an STAP or ETAP. A Universal Connector cannot end a session or redact the data returned by a query. But Universal Connectors provide information that Guardium can use for policy and auditing functions. Universal Connectors are only supported on Guardium 11.3 or later. You can use streaming APIs to perform Guardium functions. While not specifically a way to monitor data sources, streaming APIs can automate Guardium deployment and configuration and integrate these functions with other applications. This lesson was about the Guardium functionality of monitoring data from various data sources that exist within an organization. You learned about STAP agents, ETAP agents, universal connectors, and APIs. Guardium uses agents, universal connectors, and streaming APIs to gather data. In this lesson, you'll examine how each of these methods works. Effective data security requires integration with your enterprise. Guardium integrates with databases to monitor and control sessions, event management tools to exchange information about significant occurrences, your existing IT infrastructure, and third-party tools. This slide lists some of these tools.
Reviewing the methods of monitoring, you can install an agent on the data source to capture all aspects of the data connection, including the data activities that occur on that data source. This is the STAP. Then there is the ETAP, which is proxy-based. This means that the monitoring agent sits between the database and users and monitors traffic in real time. Agentless monitoring involves ingesting audit logs from cloud-based data sources. The Universal Connector reads these logs, parses the data into a format Guardium understands, and forwards it to the Guardium environment. In agent-based monitoring, the agent is installed on the server that hosts the data source or data sources. The agent interacts with the operating system to capture all the data access and connections. The agent then provides the Guardium collector, which is where the sniffer exists, with the data to perform policy correlation and analysis. Agents capture who or what is talking to the database, what sort of data or action is requested, what errors, if any, occurred with the request, and the results of the request, such as the data returned. Because the agent is tightly interconnected with the operating system and resources that the data sources use, the agent also controls the sessions and the data that is returned by access actions, such as SQL commands. The sniffer parses and analyzes the traffic from the agents, and uses security policies to control how the agents respond to the data that is collected. ETAP agent proxy monitoring is like agent monitoring, and indeed it uses the same technology as STAP. However, the agent is installed in a Docker container. It sits between the database and user. Agent proxy monitoring setup is more complex than agent-based monitoring, but it has the same ability to monitor and control sessions. You use Kubernetes to deploy the agents and can auto-deploy and auto-scale the agents. This slide will show the collector and its components. The collector receives and processes events from agents and proxy agents. The collector contains a sniffer process and a database that holds the processed events. Because there are many events, the collector must efficiently process, log, and store received events, and it must support reporting and auditing. The sniffer is on the Guardium collector. Because events might be received in a different order than the sequence in which they occurred, the sniffer organizes the received traffic. Then it analyzes the traffic, decodes and extracts SQL, and applies policy rules. Next, it parses the traffic by breaking it down into component parts such as SQL command, object, verb, and fields. Then it writes this parsed traffic to the collector database based on policy. Some events might be written while others are not. Universal connectors enable Guardium to monitor data from potentially any data source's native activity logs without using STAPs. The Guardium Universal Connector includes support for MongoDB,
MySQL, and Amazon S3, among others, and requires minimal configuration. You can develop plugins for other data sources and install them in Guardium. Universal connectors monitor sessions, requests, and errors. The Universal Connector Framework is a pipeline of plugins that are based on Logstash technology. Each Universal Connector plugin consists of an input plugin, a filter or parsing plugin, and an output plugin. Each input plugin consumes the audit logs from data sources, such as MongoDB, AWS S3, or a source that might be in your on-premises environment. The filter plugin puts the data in a format that the Guardium collector can process. The output plugin passes the audit log data to the sniffer. This slide shows universal connectors sending information to the sniffer. The sniffer processes these events in the same manner as agent and proxy agent traffic. Now you know how Guardium uses agents, universal connectors, and streaming APIs to gather data. There are limits to the amount of traffic that a single collector can log effectively. Because exceeding this limit can result in a loss of data, multiple collectors are required. The number of required collectors is based on the type and quantity of traffic you need to monitor. An environment with multiple collectors requires centralized management and aggregation. In this lesson, you learn how aggregation, central management, and load balancing work. An aggregator is a separate type of Guardium unit. It does not collect traffic directly from agents and universal collectors. Instead, each collector periodically, usually nightly, uploads its data to an aggregator. Users can view data from multiple collectors in a consolidated location. This provides a holistic view of the data and lets collectors purge their databases to free up resources. Users query the aggregator for reporting and auditing, reducing the load on collectors. The central manager stores queries, reports, policies, and alerts, making resources created on one collector available to other collectors and aggregators. Central managers provide the status of collectors and aggregators and agents. They centralize patch management, policies, user roles, permission groups, reports, and audit processes. Let's look at how you might deploy Guardium. A small environment with only a few collectors might include just one aggregator, which also serves as a central manager. When your environment reaches a size of 10 to 15 collectors, you might deploy additional aggregators, but the central manager still serves as an aggregator. With more than 15 collectors, the central manager only does management. Aggregation is completely offloaded to multiple units. Using multiple collectors also facilitates load balancing. Agents can be reassigned based on how much traffic they generate to make sure no one collector gets overloaded. Additionally, load balancing facilitates failover. The environment can be configured so that if an agent loses contact with a collector, it can notify the central manager to be reassigned to another collector. In this lesson, you learned how aggregation works with central management to provide efficient data monitoring and load balancing in Guardium. In this unit, you learned which data sources Guardium can use for active and passive monitoring, the methods used to monitor database traffic, and the basic functions of aggregation, central management, and load balancing.